We're taught that energy can neither be created nor destroyed. But in a collision involving objects with kinetic energy, that kinetic energy is often lost to other forms of energy. So it could become sound, or if it was lost to friction, it would be heat, or crumple energy to change the shape of an object. The point is, kinetic energy is very difficult to conserve in most collisions. So we use a special word in physics to describe a collision in which the kinetic energy before the collision and the kinetic energy after the collision are the same. And we use the word inelastic to describe a collision in which we lose kinetic energy to other forms of energy. And if you were asked to give examples, give heat and sound. The first question we're going to do is not an elastic collision, it's an inelastic collision. And that's due to the fact that the objects are stuck together after they collide. So there's a boy ice skating here and a girl ice skating here, and he skates into her, and they link hands and move off together. When objects that are colliding stick together after the collision, it's probably not going to be elastic, but you can always verify it using your calculations. The three things we want to solve here for this supposedly inelastic collision is the combined mass there, the velocity of these two moving off together, the kinetic energy of these two over here, the kinetic energy of the boy, the kinetic energy of the girl, and the total kinetic energy, in this case down here. So let's get to work. The combined mass is possibly the easiest. So I'll make that clear. I'm trying to say it's 80 kilograms there. M equals 80. 60 plus 80 gives the combined mass of the pair over here, and that's a total of 140 kilograms. Perhaps the next thing we can work out is the kinetic energy of the boy over here. So the kinetic energy formula is EK is equal to 1/2 times the mass times the speed squared. Since all objects are moving purely to the right, the velocity is also the speed. So kinetic energy is equal to EK is equal to 1/2 80 times 6 squared. That comes to a total of, I have 1,440 joules. Always work in kilograms and meters per second. The kinetic energy of the girl here is given by the same formula, 1/2 times 60 times 2 squared, which comes to 120 joules. So since the boy is heavier and he's moving faster, he has more kinetic energy. So the kinetic energy here is 120 joules. The net kinetic energy, the sum of the kinetic energy of both these objects, is equal to 1440 plus 120. That is equal to, let's check that, 14.5 times 80 times 6 squared, 1440, 1560. So 1,560 joules of total kinetic energy here. If we're talking about whether this collision is elastic or inelastic, we have to know whether the kinetic energy over here is the same as the kinetic energy over here, which will be given by this value here. To figure out the kinetic energy at this instant, we have to know the mass, that's 140, and the velocity. But we don't know how quickly they're moving off over here. To figure that out, we have to use our momentum laws. And that says that even if energy is lost or not conserved as kinetic energy, the momentum before the collision is always going to be the same as the momentum after the collision, supposing that no force is acted on the object from an external source. So let's figure out the momentum back here. The momentum of the boy is equal to m times v. That's 80 times 6, or 480. The momentum of the girl is 60 times 2, or 120. The net momentum at this instant here is therefore equal to 480 plus 120, or 600 kilograms times meters per second. If momentum has to be conserved, which it does, that is also equal to the net momentum over here. And that's equal to the mass of this object here, which is 140, times that mysterious velocity we're trying to work out. So 600 is equal to 140 times that velocity, or 600 divided by 140 equals velocity. V is equal to 4.29 approximately, around about. So now we know that velocity there, 4.29 approximately. We can figure out the kinetic energy, because that's equal to a half times the mass of this object, 140, times the velocity of this object here, which we figured out was 4.29 meters per second. So times 4.29 squared. 0.5 times 140 times 4.29 squared comes to 1,200, and I have 88. You might have a little bit of a different answer depending on the approximation you've used there. Thereabouts. So the net kinetic energy at this instant was 1,560, and the net kinetic energy over here is less. If you ever get an answer for the kinetic energy after the collision, which is greater than the kinetic energy beforehand, there is a major problem with the forces involved. It's either a very badly written question, or if it's on an exam, never assume the question is wrong. Always assume you've made some kind of calculation error in here, because there is a lot to work out. Since, in our case, the kinetic energy after the collision is less than the kinetic energy before the collision, we say the collision was inelastic. If it had been the same, we would call it elastic. And that energy that the objects had here has been lost as, we can say, heat and sound. In our next video, we'll look at the working out involved in an elastic collision.